password to this computer. Yeah, so in any case, so your solution would be pretty inefficient because every single time you're calling arrays copy of range, what it's doing is it's going and creating a brand new array, copying over all the elements from the portion of the array you asked for. It's giving you a brand new array, and then at the end, it's copying back over into the original memory.
Yeah, I knew that. I tried to like get rid of the copy, but it was too hard. It's like dumb.
That is actually interesting, though. If you were running out of memory, with that code, that are you having to give it command line arguments for Java to get more RAM?
No. I tried that at first because I thought it was running on memory, but then I realized that I was accidentally making infinite recursion.
Well, so typically when you're learning recursion, you'll run into a Stack Overflow exception. Did I show a Stack Overflow last time? Okay, well we'll do that really quick this time. But that's your common mistake for a recursive function is you run into a infinite loop. The equivalent of an infinite loop in recursion, where you keep calling the recursive function over and over again. And we talked last time that saves all the stuff with the call that's being put on hold. It has to save that somewhere, so that's memory inefficient. Well, if you just forever keep calling that function again and again and again and again, and you never stop, you run out of memory, and the memory behind the scenes is being managed by a stack. And Java protects your program from crashing the entire program by setting up that when your Java virtual machine launches to run your code, it gives you a cap on the RAM that it will let you use to run it. So, and it's not that much RAM. So if you're running a big scientific thing that is running out of RAM for a reasonable reason, you can give the virtual machine a command line arguments to say, I want to start with this much RAM associated with the virtual machine to accommodate the problem I'm solving. But they put the training wheels on there initially so that if you introduce a little infinite loop in there or something like that, and you just run through a gig of RAM, it hits the brakes. I think it probably only gives you maybe 60 or 70 megabytes of memory. It's not very much memory by today's standards, what the built-in thing is.
I think I just stacked workflow because I just did the two merge sort goals. I put them both in the same statement, and I had like weird logic. I don't know what else I should do.
Okay, well, let's see what we end up with here. Okay, so shut up. Lido deck back there, it's bad. We won't tell the rest of the class about your issue. No, we already covered this before class started. We're trucking ahead. All right. So let's look at this. Okay. So I have my code up from last time. Let me just copy this real quick just in case something went south. Hide. All right. Here we go. Let me just run this and make sure I don't have to restore the. Okay. So right now we have this recursive factorial that we wrote last time. So we were looking at, an introduction to factorial or introduction to recursion. Remember, recursion is when a function calls itself from within itself. We used factorial as our initial example. So like factorial of 5 is 5 times 4 times 3 times 2 times 1. Or if we want to think about it recursively, we say factorial 5 is equal to 5 times the factorial of 4. So now we got to wait for the answer of the factorial of 4. Factorial of 4 is 4 times the factorial of 3. Now we got to wait for the answer of factorial of 3, so on and so forth. All right, so every single time we have to wait, the current call to factorial that we're in is going to have to get put on hold, put on a shelf. I think we were doing it like 20-pound weights over here last time. So it gets put on some shelf while it waits for the answer to the next call. So 4 factorial cannot finish until it has the answer of 3 factorial. And 3 factorial can't finish until it has the answer of 2 factorial. 2 factorial can't finish until it has the answer of a 1 factorial. So on and so forth. All right. Now, eventually, if you look at the code we wrote last time, we have a stop case. So our stop case is, so we're going to keep calling factorial recursively right here until we finally call it with an n, an input of 1. And when we finally give it an input of 1, we're going to just return 1. The factorial of 1 is 1. What does the return keyword do? Yeah. It optionally returns a value, which we are doing now. But more importantly for us, it makes a function immediately end, which means we will never get to this code here if we got to this line right here. Make sense? We won't hit that code another time. Therefore, we won't call factorial recursively that one last time. All right. So since n is 1, this stops it. And then, so we have, we got the answer for factorial of 1, which then allows us to get the answer to the factorial of 2, which then allows us to get the factorial of 3, which then allows us to get the factorial of 4, which then finally gives us our final answer if our example was 5 factorial. Go ahead.
So you're highlighting return work in my mind. That makes me think that, like, even though we're doing the right calculations at the end, whatever we get, if it's equal to 1, it's going to return 1.
Yeah, this one copy of the function. We called 5 copies of this function. And we had to keep putting those copies on hold until we could finally get our answer. Yeah. Yeah, because we never get into this if statement. Return makes a function immediately end, but only if we get to this line. We only get into this line if the value that was passed in was 1. So when we call factorial recursively on 5, is 5 equal to 1? No. So we'll skip past this entire if statement and get right here. Next time, we're calling a factorial. So if we originally call it with 5. So we pass in 5 factorial. Is 5 equal to 1? No. So we're going to return 5 times whatever the factorial of 4 is. Well, because we're calling factorial recursively, which is the same function. Yeah, that's recursion. So recursion is when a function calls itself from within itself. And so that means that this call to factorial recursion, the original one, if we use a 5, that guy cannot actually give us an answer. This line right here is not going to actually spit out an answer. We know the value of 5 the first time. The value of 5 is 5. Then we need to multiply that, and we're going to multiply that by whatever the call for factorial of 4 gives us. So we have to sit there and wait for that guy to finish. And then, so that's where we kind of put the factorial of 5 up on a shelf and say, okay, chill here for a bit. I don't have the answer to the factorial of 4 yet. So we're going to go ahead and call this function again on the factorial of 4. Factorial of 4 bypasses that first if statement. It gets to return 4 times the factorial of 3. Well, now this guy has to wait because we have to wait for the answer for factorial of 3. So we put this on the shelf. So now we have 2 calls to that function that are just waiting for answers. So now we're at the factorial of 3. Is 3 equal to 1? No. So we drop past that if statement. We return 3 times the factorial of 2. Well, now we have to wait for the factorial of 2, that answer. So we put the factorial of 3 up on the shelf. So now we have 3 guys sitting on the shelf that can't finish because they're all waiting for answers. So now we're on factorial of 2. Is 2 equal to 1? No. We skip past that. We return 2 times the factorial of 1. We have to wait for that answer. So we take that guy, we put it on the shelf. So now we have 4 copies of factorial sitting on the shelf here just waiting for their answers. We're waiting for factorial of 4, factorial of 3, factorial of 2, and now the current thing we're on is factorial of 1. Is 1 equal to 1? Yes, it is. So we get into this if statement, we get to this return statement there, we return a 1. So now that we have that 1 and we don't have any more recursive calls, we're able to get the answer for the factorial of 2. Which then allows us to get the answer for factorial of 3, which then allows us to get the answer for factorial of 4, which then allows us to get our final answer for factorial of 5. So all the recursion unwinds, and we're finally able to return our answer, which was our very first time we called this line. but it's the very last line that finishes as our recursion unwinds. Good.
I could be overthinking.
I'm sure you are. I'm almost positive, actually.
Actually, I'm not. My question is just like when we're doing the putting on the shelf, et cetera, that analogy you gave, why do we return one instead of the answer that we give?
That is the answer.
It is.
The answer of factorial of 1 is 1.
Well, yeah, that, but.
Well, that's the only time we're ever returning 1. We only ever return a 1 when we're calculating the factorial of 1. Under all other circumstances, we return the factorial of the current value. Well, we return the current value times the factorial of that value minus 1. That's what we do in every other situation other than when we're figuring out the factorial of 1. All right. So just to give you the example of running out of memory, we can actually probably just do it by giving it a big number there rather than taking our if statement out. So I'm going to try to get the factorial of 50,000. Let's see, because that's going to put 49,999 copies of this function on that stack. Let's see if enough of our default memory allows us to hold that many copies of it. I don't think it will, but let's find out. Yeah, we got the error up here. I'm scrolling up to where we first died. It'll be a stack overflow exception. Ninja. It doesn't scroll that far. Okay, well let's
Catch it.
oh, I could do a catch on it. We'll do that here in a second if this doesn't fly. All right, that ran out of why am I getting a 0 now? I'm calling recursively of my solution. Make sure this guy's still working. Some point there, it couldn't call the thing anymore. Let's just make sure it's doing decent.
Tap out. Answer.
Yeah, so let's go with 10. Let's see at what point it stops functioning. Okay, so you're already seeing factorial 10 is getting to be a pretty big number. So let's do 20. Oh, okay. Hold on. Tell me why that's a negative number. All of you are in computer architecture right now, right? You may not have gotten to this this stuff yet, but I've covered it in class. Good.
Could it potentially be if you get to like the highest point that, or the highest number, it just becomes negative, I guess? Like I know.
Okay, the answer is yes, the answer is right. Let me give you an example. So if we're dealing with a signed whole number, and let's say we're dealing with a byte. So a byte is an 8-bit signed whole number. So it holds plus or minus 2 to the 7th power, roughly. You'll learn in architecture that the way you store negative values is through something called 2's complement. So you won't store a positive and a negative 0. You'll just have 0. You don't need to store a positive and negative 0. 0 is 0. So instead, you'll have one extra value on the negative side. So the range of values that fit inside of a byte are negative 128 to positive 127. So if you have a byte whose value is 127 and you add 1 to that, you end up with negative 128. Why? Because 127 on the positive, it's where it starts. It's because when you add 1 to this, you get overflows across the board and you end up with 1 with all zeros, which is negative 128 encoded in 2's complement. It'll be the same thing. It'll just go a much higher number. So if you're dealing with a 64, it'll be that 9.3 quintillion number or something like that. For an int, it'll be 2.1 billion. So 2.1 billion plus 1 gets you to negative 2.1 billion. So you can actually add one to a number indefinitely inside of a computer because it always wraps back on itself, not because there's some if statement, but it's because that's how binary math works. If you only have 32 buckets to hold zeros and ones, and you add one to it and you end up overflowing where you really needed 33 buckets for the next number, what ends up happening is it circles back to the number that you have represented is the smallest negative number that we have because your real value fell off the end in just doing binary math when you didn't have enough buckets to do your math. So it's just kind of more of a interesting trivia thing. Yeah. Mm. Potentially. Yeah. In old video games, when they still would have been concerned about memory, I mean, right back to the Y2K thing, an old video game may have said, oh, well, we're going to store score as a short. Yeah. So maybe the largest value, and maybe they decide, okay, I'm going to store it as an unsigned because your score wouldn't be a negative number by default or something. Although if you see it go negative, then they're storing it as a sign. So that means the largest value be 32,767. As soon as you added one to it, you'd have negative 32,768 as your score. So that's if they use the 16-bit value for score or something like that. But absolutely, if you saw a negative number for your score in an old video game, it's probably because of this principle. All right. Last question, then we're diving into merge sort, and there'll be all sorts of new questions. Go ahead.
What would you call that range value that we hit it becomes negative? Is that like he says something about 64-bit?
Oh, I messed up. I meant 30.
No, it doesn't matter. I mean, those are a 64-bit value is a long, 32-bit value is an int, 16-bit value is a short, 8-bit value is a byte. Yeah, so each one of those, when we talked about that as our primitive types, we talked about this as, back then when these languages came out, memory was really, really, really expensive. So we had to be careful with how much memory we used for stuff. So they gave us multiple options for storing whole signed numbers so that we could pick the one that was big enough to support what we were trying to do, but small enough to not be wasteful of memory. Where now we just put everything in an int and it doesn't fit, we put it in a long. If it doesn't fit there, we just move over to one of the object classes. In Java, we have a class called big integer that lets you just create arbitrarily huge integers and it just slows down as they get giant because you start using up your computer memory. All right, so let's go into merge sort. So I mentioned this last time, and we're going to use something relatively small. So let me draw. So we're gonna have a 6-bucket array. Why won't it center under that? You're killing me. All right, let's go with that. All right, so this is bucket 0, bucket 1, bucket 2, bucket 3, bucket 4, bucket 5. All right, and then we're going to put some numbers in here. So we'll say 4, 1, 7, 3, 2, 8. All right, so can we all agree, as humans just glancing at that, these are not sorted? All right, so now the first thing I want to make a distinction between is our ability to look at a list of numbers and say those are not sorted versus a computer's ability to glance at a set of numbers to determine if they're sorted or not. All right, we can certainly dive in with a computer and write a program that walks through to make sure they're sorted. But if we're considering, can a computer just glance at a set and say, is this sorted or not? If it's not sorted, maybe I need to do something about that. But they need to be able to, quote, glance at it for merge sort. All right, so if we are looking at this whole collection, as humans, we can say that this is not sorted because we kind of even though we didn't think about it, we kind of just glanced through them and we saw that very quickly there was an occurrence where there was a smaller value that came after a larger value. 1 and 4 are not even sorted. We can just stop right there, right? So this is not a sorted thing. All right, so now what does merge sort do? Merge sort glances at this and says, this is not sorted, so we need to fix that. Now, if you're a computer and I'm trying to mimic the idea of glancing at something and determining, is this sorted or not? And here I'll even give you a hint. How can a computer determine that a collection is definitely sorted at a quote glance? Go ahead.
Is it possible that every value looks like greater than before?
Well, but at that point, you'd have to do logic. I'm saying at a glance. And it's a tough equivalent to say with computers. Is it true that if I give you exactly one value, by definition, that's sorted? It's a sorted thing, right? If I give you a single value. So from a computer's perspective, if they're only paying attention to one element, they don't even have to look at the contents. They can just say that is sorted, right? We would call that trivially sorted. All right, so right off the bat, we ask the question, is this list trivially sorted? Is it a one list? Right now, this is a list containing how many things? Exactly how many things are in this list? 6. All right, so, and if this guy was stored inside of something, maybe AR. So we say AR equals this guy. So we would say that the length of that guy is AR.length, right? Which we know is going to be 6 in this particular example. All right, so since AR.length, well, since the length of what we're looking at here, what we're looking at here is the entire collection. So since the entire collection, which has more than one element in it, is not by default sorted, we need to go and do some stuff. So what are we going to do? We're going to say, let's go ahead and divide our collection in half. And let's sort the left half, and then let's sort the right half. And then we'll do this, what's called a merge step for merge sort after we get that arranged. And the merge step, it takes two lists that are sorted in and of themselves and merges them together into a new list that has all the numbers in the right order. That's what that merge step does. And we'll see the algorithm for that. All right, so we're going to look at this. We're going to say, okay, well, this portion of the list starts at bucket 0, goes all the way to bucket 5. That is a list containing 6 elements. All right, so we need to figure out where the middle of this is. So we're just going to do this as humans right now, so it's quick. So we're going to say, okay, well, if I'm going to divide this list in half, that is the first half. And this is the second half. All right, we're all good with that? All right, now this guy over here, he's going to get put on hold for a while because the first thing we're going to do, I mean, ultimately, if I want to sort the left half and the right half, and we're in the middle of writing something called merge sort, so we're creating a function here called merge sort. This guy sorts stuff, assuming we write it right, right? So we got this tool we're working on that sorts stuff. So we're going to say merge sort, go ahead and sort the left half. Merge sort, go ahead and sort the right half. That'll be like line 5 and line 6 right after each other. Call merge sort again. This second call to merge sort is going to have to wait a while before he even gets called. Because that first call to merge sort, the guy right over here, that call is going to look at that and say, is that trivially sorted? No, it's got 3 elements in it. This call to merge sort starts at bucket 0 and ends at bucket 2. Okay, so since beginning and end are not the same number, it's more than one value big. Therefore, by definition, it's not sorted. All right. So now what we're going to do is we're going to split this in half. Now, depending on how we do the math, splitting this in half, it might mean two different things, but let's just always make the big half the second half for right now. So splitting this guy in half is going to mean getting this piece and getting this piece. Let's do that. Okay. Now, so those are our two halves for that guy. So now the first call to merge sort, we're going to call merge sort in the left half. We're going to call merge sort in the right half. So remember, we called merge sort once to get initially into this. Then we have a call to merge sort here and a call to merge sort here. And this guy hasn't even gotten called yet. Then we have a call to merge sort here and a merge sort here. And this guy has not gotten called yet. So we're currently in this merge sort. So we have multiple calls to merge sort, right? We call merge sort whenever we need to sort a portion of the list. That's what merge sort does. This is that recursive thinking. I need to sort something from bucket X to bucket Y, from bucket begin to bucket end. No problem. Pass the array in with the portion of the array that we should be focusing on and let merge sort that in whatever way merge sort does. We haven't even gotten to the sorting part. We've only gotten to the part of detecting unsortedness, right? So now the question is this guy sorted? 100%. Begin and end are the same value he sorted. So this call to merge sort is over. Now we can make this call to merge sort. We ask, is this trivially sorted? No, it's got two elements, right? Begin is 0, end is, or begin is 1, end is 2. Not the same value. So we're going to call merge sort on the first half and call merge sort on the second half. Then we say, is this call sorted? So one list, begin and end are the same value. They're both 1. So that call to merge sort is done. Then we'll make our second call to merge sort. Is this guy sorted? Yep, trivially sorted because begin and end are both 2. So we don't have to do anything here to sort it. We're saying we're done. The one list you gave me is sorted. I've done my magic hard work for the day. I can go home, kick up, play whatever the latest, coolest game is, blah, blah, blah. So that guy's done. So now the 2 calls we made to merge sort when we got here, what we called merge sort on the left half and the right half, have now finished. So now we're back here. We have now completed our first and second call to merge sort at that level. Now we have to do the merge step. All right. So I'm going to just copy that guy here. We're going to create another slide. Merge step. Right. So we got our merge step there. Oh, I want to look at something here real quick. Oh. Wonder where Nathan is tonight. What am I doing? Hide, right? All right. What's up? We're about to slam into that. So it comes down to dividing it up enough times to get to a trivially sorted position. So most, which is 1. Then we bounce up. So right now we're about to see the simplest version of the actual sorting. So we only sort if the list is a 2 list or bigger. Now we probably could add a little optimization in and say something like, if the difference between the beginning and end is 1, we know we're dealing with the 2 list, which means we know we're wasting our time with 2 merge sort calls because they're just going to bounce right back to us. So we could choose not to make those 2, the left half and the right half merge sort calls on a 2 list because we know those are going to be trivially sorted. We could cut it off at the knees 1 step short, but we'll just keep rolling with it. It shows the full algorithm without us having to make an exception case. All right, so we hit those 2 1 lists. We now bounce back up. So we have completed the first and the second merge sort call at this level. Okay, so now at this level, I'm going to put some variables in here, so this will kind of backfill what our functions might take. So we're going to have begin 1 and begin 2. Space these guys reasonably. And then we're going to have N2 and N1. All right. So you have a couple of variables here. And in this particular call to merge sort, these guys would have had these values. Begin 1 points to bucket 1, not bucket 0. This is where that your situation would have been if you're passing it brand new arrays as opposed to the original array. So the first element of the portion of the array that we're getting ready to sort here actually is not the very beginning of the array right now. The fake beginning is actually bucket 1. The fake end is actually bucket 2. So we're only sorting that one little window inside the array. Eventually we'll sort all windows, but that's all we're working on right now. All right, so we have those two guys. And then we have begin 2 is here. And N2 is here. All right. So in the simplest case here, begin 1 and N1, begin 2 and N2 are they're the same value in this particular case. Now I'm going to create a couple of other variables just to be really verbose here. So we're going to call this pause 1. Actually, let's call this pause left list. And we'll call this guy pause right list. All right. So we're going to make the assumption that we are not going to make changes to begin 1 and end 1. We're just going to let them be like permanent markers at this particular call, marking the beginning and ending of the left and the right lists. No problem. As we're doing this, we could have made updates to begin 1 and not used our pause, but we'll go ahead and use the pause thing just so we keep those things separate. All right, and you'll see what I'm going to do with it here in a second. All right, so we're going to make pause left list point to the current at the beginning, the current beginning of the left half. And we're going to make pause right list point to the beginning of the right half. All right, so now the merge step goes like this. First of all, we are going to, we are going to do this here. I'm going to put this over to the side. We'll call this guy answer. All right, so what I'll do is I'm going to create a brand new array, an empty array, that's big enough to hold the number of elements that we are sorting. Make sense? Because as I'm sorting it, we're going to have a whole bunch of little competitions. So we're going to be saying, which is the smaller number? The number that pause left list is currently pointing at, or the number that pause right list is currently pointing at? Which is smaller, a 1 or a 7? A fight to the death, 1 beats a 7, right? So what we'll do is we need to put that 1 somewhere. We need to record these values in order as we're getting them. We don't want to overwrite the values in the original array yet. We want to get them in order over here and then go back and overwrite them in the original array. Otherwise, we're going to be destroying values as we're going. Go ahead. We are.
Why then go back home, right?
So that at the very, very, very beginning, when all is said and done, when we get up to do the merge step at the original call, what's going to happen is this portion of that array will already be sorted. This portion of the array will already be sorted. So our original array has transformed into this array prepared for the final merge step. Does that make sense? So we're making these changes to the original so that we go back and we're losing them. Going down. Oh, I'm a professional. My wife falls asleep in the middle of conversations. My mom recently fell asleep in the middle of a conversation, but she's old. And she asked me a question. I was 5 seconds into answering it, and she was out for an hour. Just pathetic. I told her that. I let her sleep, though. All right. So that's the ultimate goal is we're going to have each of those sections end up being sorted in their own little area of the original array. All right. So as we're sorting this guy, we're going to have little fights. So we're having whatever pause left list is pointing at compare itself to whatever pause right list is pointing at. So pause left list is looking at the number at bucket 1. Pause right list is looking at the number at bucket 2. So we compare a 1 to a 7. Which one should come first? A 1 should come first. So actually, let's give ourselves another value over here. Let's call this guy curpause. Curios. Okay, perfect. Curpause. And we'll have that guy point here. So curpause is going to point at the bucket that we're currently about to declare the winner for. So curpause will place the thing at bucket 0, then curpause will increment because the next number we're placing is the guy who's in bucket 1. Second place. Make sense? All right. So we decided 1 versus a 7. The 1 wins. So we'll take the value that lives at position pause left list. Now keep in mind, I am talking through the algorithm out loud. This might be helpful for you as you are doing your homework assignment. All right. So we're going to take the number that pause left list is pointing at, compare it to the number pause right list is pointing at. We make the determination that 1 is smaller than 7. So the number that pause left list is pointing at is our winner. So we will take the number at bucket pause left list and place it in answer at bucket curpause. So we'll put the 1 right there, and then we will increment curpause. Now, we also then need to increment pause left list. Now, what can you tell me about the current situation with pause left list? I just added 1 to it. It currently points to a 2. What is the problem with pause left list as it relates to the left list right now? Yeah, it's walked off the end of the left list. We have finished finding winners from the left list. So since the pause left list is greater than end 1, it's no longer even in the competition, right? So next thing, we know we're not done finding winners yet because curpause still points to a legal place on this list. So we can use curpause relative to answers length to tell us whether we have more winners to find. All right. Then we have to say, okay, well, is this a 2-man race? Am I comparing 2 actual numbers, or is only one of them currently even still running? That make sense? All right. So right now we're going to say, do I have another number to place? Yes, I do, because curpause is not off the end of answer. So then I come back over here. I say, okay, now let's compare some winners. First of all, is pause left list and pause right list, do they both point to legal places on the list? No. Pause left list has walked off of its left list, right? Because it's greater than end one. So begin one and end one, they keep track of the beginning and ending of the left list. End two and begin two keep track of the beginning and end of the right list. So since pause left list has now gone past end one, it no longer is pointing to a valid location on the left list. So it's no longer in the game for picking winners. So the first question we're going to ask in the merge step is we're going to say, are both pause left list and pause right list legal? If they both are pointing to real places on their half of the list, then we're going to have our real competition. So if they're both legal, like they were on the last loop through, we compared the 1 to the 7 because they were both legal. But now we already declared one the winner, the overall winner, right? And we're going to go back and keep in mind here that the left list and the right list are sorted in and of themselves when we're at this point. That's not all that impressive right now because they're only one lists, but it will become more impressive as we move up the list. All right. So we say, are they both legal? They're not. At least, well, they're not. One of them must be illegal. So now let's ask a question. Is pause left list legal? We know they're both not legal. So we know at least, we know one of them is illegal. So we can either ask the question, is left list legal or is left list illegal? And depending on which question we ask and the answer, we know whether to just take the left guy as our default winner or the right guy as our default winner. So let's just ask the question, is pause left list still pointing to something on the left list? No, it's not. And the only reason we're even asking this question is because we've already determined that they're not both legal. So that means one of them is illegal. So we'll ask, is left list legal? Nope. So right list must be the legal one. So since right list is the legal one, we will just say, 7, you are by default the winner. We'll place you at position cur pause and answer. Then we will increment cur pause. Now, because cur pause just went off the end of our temporary array, we know we're done placing winners in this portion of the race, this little portion of the list. All right. So that means I no longer have to compete, have guys compete against each other, which means that I can now safely change the contents of those two buckets in the original list because I'm done using them for doing the competitions. So what I'm going to do is I'm going to write the code that loops through every element of this list, which is the same length as this list over here. I hate that. Move. Okay, it's the same length as the list over here, but not necessarily the same indexes. Special note, this is a point of complexity in your program. You are going to be placing whatever is at bucket 0 in this case into bucket 1 of our original array, because that's the portion of the array we're dealing with. You will always be dealing with a 0 indexed array over here because we created it as a temporary thing, right? We said, okay, I have a 2 list I'm supposed to sort. I don't want to damage this stuff here initially by overwriting stuff. So instead, I'm going to go ahead and create a brand new temporary 2 list, and I'm going to fill that with my winners. And then once I'm done picking winners, I'll copy the contents of that back into the original list. So now that portion of the list is sorted in and of itself. That's all we're accomplishing here. All right. So we go ahead and we overwrite the original contents. We overwrite bucket 1 here with whatever is bucket 0 on this one. So that's our 1. We overwrite bucket 2 here with whatever was at bucket 1 here. So that's our 7. In this particular case, it didn't actually require us to overwrite, but we don't check that. We just say, we know after our races are over, this guy is sorted. we know how many elements are in this list and where the beginning is. So just fill up that part of the original list with our sorted version. You don't have to check anything anymore. You know exactly where the begin and end is of both of them. We know the beginning of this one is 0 and the ending of this one is answer.length. We know the beginning of this one is 1 and the beginning of this one is begin 1 and the ending of this one is end 2. Right? That's why we're keeping track of so many variables. I know that can be intimidating, but it actually makes the problem easier if you don't try to reuse the same variable for 3 or 4 different things. It technically works, and if you're an advanced programmer, you might just do that real quick. But as we're drawing pictures here, none of the individual steps we're doing here are very difficult, right? There's just a lot of little stupid steps that we're having to do. And you'll find that easier if you draw pictures like this and you keep, we are not touching where the beginning and ending of our lists are. Those are basically hard-coded variables. We're never going to touch begin 1 and end 1 or begin 2 and end 2. That way, at all times, as we're in here, we know where the left half begins and the left half ends, and where the right half begins and the right half ends, and we know the constraints on the entire portion of the list we're in. All right. So instead, what we're going to do is we're going to keep track of where we're at in the race from the left and the right half with these 2 numbers, and then also where we are in this array with this extra variable. All right. So when all is said and done, we copy this guy over. We now know that this portion of the array is sorted, which now means we can actually jump back up here. So this guy has now been reordered, even though it didn't technically change it in this particular case. Make some sense? Are we good with that version of the step? We're going to keep going, and as you're going to see it get more complex. So far, the easiest version was trivial. Every one of you could write that right now. In my defense, I told you this weekend was going to be hell. But I promise you, this is such an important assignment. You are supposed to talk to your classmates on Tuesday. All right. This assignment, I mean, it's not hard once you have a competency in this stuff, but it's going to be hard for most of you right now because so many things are happening. I promise you it's not hard, but it's going to feel impossible. You're going to cry. By the way, if you cry, you should take a video. That should get sent to me. Okay, now I feel like I should pause the recording, but we're just going to roll with it. I do have collections of cry pics from students. I have collections of puke pics from students. Hey, you got some students that aren't very trustworthy. They say, "Oh, I'm not really feeling well. I've been throwing up all morning." Let's picture if it didn't happen or it didn't happen. I have all of them. I have students from years ago. I don't put them publicly.
Is that what gives you motivation to keep teaching?
I don't know. I find human misery entertaining in the moment. Like I don't want anybody hurt, but I do want them to suffer to make themselves stronger. So I mean, the goal is positive. Like I don't want to just see someone suffer and just end up in the gutter. That's not the kind of suffering I want. But if life is all, daisies and walks in the garden, then, and you're never actually thrown up against a real hard problem, you're never going to learn anything. And what's going to happen is a year from now or 2 years from now, you'll look back at this hard problem and say, oh, well, that wasn't that hard because you got so many more reps under your belt. But right now, your weekend's going to be ruined, and those cry picks and actually, frankly, potentially puke picks sometimes give you a friendlier grade. So special consideration might be given for special circumstances. Let's go with that.
So we get extra credit if we cry.
I'm not specifically saying you'll get extra credit. I feel like that might violate some ethical things. You just might be looked upon favorably due to my compassion. In this dojo. All right. So let's keep trucking because you're going to want as much of this as possible for your assignment, right? What's he doing? Well, now but I mean, that's not even all that original, original. I was entertained when he sent me when he was going to miss a class near, was it Thanksgiving break? When he sent me the stock AI email with all the brackets still in it, dear, insert professor name. I will, and he made it so generic and stupid. That made me laugh. Those are things that can only help the way I view you in a borderline grade situation. I think that works. I think that's ethical. Yeah. Anything that's on recording, we got to make sure is good. All right. So we're now done with our first call to that list, right? So we finished. We made a call here. Then we made a call here to merge sort. We made a call here to merge sort. Both of those calls returned. I did my merge step, which now has that portion of the list in order, right? We also know that this portion of that list is already in order. So actually this was our first call from this 3 list. This was our second call from this 3 list. So the first call came back already sorted because it was a 1 list. The second call came back now sorted, even though we happened to recognize that it was already sorted just by luck. But it's now come back sorted. So we're done with our second call to merge sort. So now what do? We do our merge step on this list. After we finish our 2 calls to merge sort left, merge sort right, we come back from that. We know that the left is now sorted, the right is now sorted. We're going to merge them together. And then we're going to finish. So now we're going to take this list. We're going to come down here. Let's see. What's your preference? Do you want me to overwrite the contents of this slide for this 2 list and just slot in the 3 list? Or do you want me to make a brand new slide for that one? All right. So I'll create another slide here. It's going to have all the same variables on it because we're doing the same algorithm. I'm just showing the next version of this. All right, I'll copy my 3 list here. So we'll get rid of this guy. Oh, Ninja. Get rid of this guy. There we go. All right. We need to make sure we update all our variables. So begin 1 and end 1. Oh yeah, I had to make a whole bunch I was on Fox News yesterday being interviewed for our Boodlebox AI thing. Huh? I was. Well, yeah, they always bring the talent on the news story. So I'm there in my my Ghostbusters shirt, and that was the first part of the whole interview is who's that guy in your shirt? I think you could probably look it up. It's like Fox News live hour or something like that.
What station you aired on? Yes, Fox.
I've been on TV a lot of times. Just it's kind of a thing when you're famous.
We have to see some of the professional eating contests.
Well, you can Google it. Look up awesome fat big beef paradise.
Big beef paradise.
Huh? I couldn't eat that much anymore. My has been. Huh? Okay, what's on the table? What are we fighting for? If I have to win, I would beat you. But I wouldn't out of comfort. All right, let's keep trucking. All right, so we're going to keep track of the begin and end of the left list. We're also going to make pause left list point to the beginning of the left list. Now, our left list is only a 1 list again. We'll make begin 2 point at the location of the beginning of the second list. And we'll make end 2 point at the position of the beginning of our second list, or the end of our second list. And we'll make pause right list point at the beginning of our second list there. Then we'll create our temporary list. Now, in this particular case, we happen to be dealing with index 0 through 2 on the real list, as well as 0 through 2 on the other list, because we're dealing with the far left, right? Rarely will the portion of the list that you're looking at be index 0 through something. You're usually at some subsection of the list. So typically this list here and this blah, 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 and this list over here will not have the same indexes. This guy will always be 0 based. This guy will be wherever it is, wherever begin one is. All right. So we create our temporary list that is the same length as the portion of the list we're dealing with, and we start playing our game. We say, our pause left list and pause right list, are those both legal? Yes, they are. Okay, so we say, which one's smaller? A 4, which is what pause left list points at, or a 1, which is what pause right list points at. Which one is the smaller value? A 1. So we'll go ahead and place the 1. We'll increment curve pause so we know where to put the next guy. Then we'll increment pause right list because that's the guy that won that race. All right. Then we loop back around. We ask the question again. Well, first of all, we say, are we out of things to place? No. Curve pause still points to a real place on the temporary list. So we come back over here. We ask, is pause left list, does that point to a real place? Yep. Does pause right list point to a real place? Yep. So they're both still on their respective lists. So now we ask the question, who wins? Who wins between a 4, which is what pause left list points at, and a 7, which is what pause right list points at? Who wins? 4. So we'll go ahead and place the 4. We'll increment curve pause. Then we will increment pause left list because that's the guy we just placed. That's our winner. All right. And then we say, oh, do we still have more to place? Yep, because we're not done filling this array yet. Go ahead.
We get 1.
Because curve pause at the beginning pointed at 0. And left list, pause left list pointed there. And pause right list pointed here. We asked ourselves, are both of these variables pointing to real locations on their respective lists? Yes, they are. So we compared the 4, the number this guy points to the 1, the guy this points to. We saw that 1 is less than 4. So we placed the 1 at where curve pause was. And then we said, okay, well, we just declared this guy a winner, so we're going to move down this list. Then we ask the same question again. Are they still legal? Yes. Who wins between a 4 and a 7? A 4. Place the 4, increment this. Then we increment this guy because the 4 was just placed. Now we spin back up. We ask the question, are they both pointing to legal places now? Nope. Pause left list has now walked off the end of its list. Why? Because it's now greater than N1. N1 marked the right portion of the left half of the list, and we have now walked past that. Yeah. Yes, but begin 1, N1, begin 2, N2, they will actually be parameters that get passed into your merge sort call. Because when you call merge sort, you're going to say merge sort this array in this range. Since we use merge sort for all sorts of things. So originally we'll say call merge sort on the range of 0 to length -1, the whole array. Then we'll call merge sort twice on the first half and the second half. So we'll have to be passing in begin 1, N1, begin 2, N2. And those would be the 4 integers that we'll calculate. And I'll give you a hint. Begin 2, that's the tricky one. Begin 2 is the one that you need to pay attention to your math. So, because begin 2 is not the length divided by 2. or the length divided by 2 plus 1, depending on how you divide your lists. If you make the left half the bigger half or the right half the bigger half, it's not that. That's not the math. So it's not length divided by 2, because that will give you the middle, that'll give you the beginning of the right half in, if you're dealing with the entire list 0 indexed. But if you're at the right half of the list and you're looking at like buckets 6 through 10, and you take the length of that 4 and you divide it by 2, you're at bucket 2. The right half, the beginning of the right half of this list is not over here at bucket 2. Make sense? So that math is not the right math. It worked when you were dealing with the whole list, because that took you to the right middle. If you were dealing with bucket 1 and bucket 10, well, it's got a length of 10 divided by 2 is 5. This is the middle of this guy. Everything looks good. But if you're dealing with 6 to 10, and you say, oh, well, that only has a length of 4. 4 divided by 2 is 2. The middle of this guy is not this guy over here. So you'll have to figure out what is the math that consistently gets me the middle of these guys. Not hard math, but it's different math than the length divided by 2. All right, there's your hint for calculating begin to. All right, so we asked the question here, is pause left list, is it a legal position? It's not. So both of them are not legal. So now we know one of them is legal and one of them's illegal. So our next if statement will say, well, is pause left list legal? Nope. Okay, well, we only have one more option. Is pause right list legal? Yes. So by default, he's our winner. So we'll place him here. We will increment this guy. We will then increment our winner. We know we're done placing stuff because cur pause has walked off the end of this array. We also know we're done placing stuff because pause left list is off the end of the left array, and pause right list is off the end of the right array. Pause left list is greater than N1. Pause right list is greater than N2. Okay, so then we have our answers. We now copy them back over the original. So this will be 1. This will be 4. This will be 7. So we did make changes to this one, right? All right. Now we made those changes in the original memory, which means back here, this has become 1, 4, 7, which means this has become 1, 4, 7. Because these are all the original memory. So now this call to merge sort, the original first call to merge sort, the merge sort that we called on the left half of the full list has now just ended. So at this point, the entire right half of our list is sorted. But we haven't even done the right half yet. So we're going to go down the path of the right half. We're going to do the exact same thing. We'll call merge sort. Well, we'll call merge sort in the left half here. We'll call merge sort in the right half here. Left half is already sorted. Right half will pass into merge sort. We'll do the merge step. Oh, well, actually, it'll pass in. We'll do the one list. They're both already sorted. Then we'll do the merge step on the 2 to the 8. They happen to already be sorted, so we'll pretend like we already returned from that merge step. We now need to do the merge step on this guy. So that will end up changing this portion of the array to 2, 3, 8, which also changed it up here to 3, 8. So this call to merge sort is now done. So now we see that the left half is sorted and the right half is sorted. So we do our call to merge just like we did before. Here, I'll actually. So here's our final call to merge sort. Well, actually, we already made this call to merge sort. This is our final merge. After all the merge sort calls have bounced back. All these guys are empty. We place begin one and end one. Begin one is here. End one is here. Podcast left is, or pause left is here. Begin two is here. End two is here. And the beginning of pause left, or I'm sorry, pause right. So pause left goes, oh, I just moved pause right. So pause right will be here. And that points to this guy. All right, so there's my setup. So we do our normal competition. So this will be a 1, then a 2, then a 3, then a 4, then a 7, and now we're off the end of the left list. So by default, 8 wins, which means this becomes a 1, a 2, a 3, a 4, a 7, and an 8 once we copy back over, which then makes this guy up here in the original memory a 1, a 2, a 3, a where's my values? Right there, and merge sort's done. That list is now sorted. Make sense? Your homework is to write merge sort. You'll create an array with some number, or just fill it with random numbers, an array of 10 buckets, or however long you want it to be. It should work for any length. You could fill it up with random numbers. You could hard code numbers. I don't care. Just make sure you code it in such a way that you're actually testing whether your code is working. So display your list beforehand, your array beforehand, and display it afterwards. I'll give you, well, I'll make sure that the slides are linked. I think they are, but I'll make sure that I'll put the assignment up on Canvas, and that will be due on Tuesday before class starts. Question? Oh, that was a question. All right. Questions, comments, concerns, bribes. Go ahead. She's so used to raising her hand, she'll just raise it like I don't actually have a question. This is kind of like a.
Oh, but I have one that's not.
Well, really, most of your questions,